today I wanted to quickly talk about a automatic differentiation tool for C++ using the Clang frontend, and we call that tool Clad. So the motivation for our work is essentially that we want to provide automatic differentiation for C and C++ that works without code modifications, including legacy code, which in the field of high-energy physics, we have a lot. And also, we don't want to modify it. So the typical compilation pipeline, the Clang compilation pipeline is you feed normally code to something that's called a front end in the compiler, and then it would produce some intermediate representation, which is in the case of Clang an abstract syntax tree, which oddly enough, it's neither abstract nor syntax nor a tree. It's more like a very concrete semantic acyclic graph. And then the Clad would transform that AST into either something that goes to the Clang backend, which generates code, or it would write a bunch of code in textual form into a file, and then from that point onwards, you can use your favorite compiler implementation to create the derivatives. So to compile the code. So we support partial and higher order derivatives. We support gradients, Hessians, and Jacobians. We also provide low-level derivative access primitives, and we also allow being embedded in frameworks. So in that direction, I will be showing a few examples. So the main example is the usage, the programming model of how you would use Clad at the moment. So we can see that we first need to include a special header file, which nowadays is also useful. It's also possible to just use a pragma handler to enable it. And it would essentially take a power of 2 function, which returns x times x. It would produce a function which is derivative of that power 2 underscore drx0 of double. That derivative can be accessed in 3 ways actually. From the first, you can use it as a standard forward declared function, or you can use it as this functor-like wrapper object where we can call execute or get the function pointer itself, so that we can use the raw function pointer. And the last way is to just forward declare the result and use it. So those are the 3 different patterns, and you will see a few patterns from those, actually 2 patterns that are used and in their use cases. We are working on supporting CUDA code, and this work is done mostly by Ioana Ifrim. And here we are showing the way that things currently work. So the examples of power 2 translated into CUDA code would essentially use the generic CUDA memory allocation model. Then we would call the differentiate on x. This would then create a bunch of things. So we need to somehow transfer the function pointer that's differentiated from the host to the device. Then through the static pointer, we will use the definition that was provided already by Clad. And then we will call the compute, which is the scheduling function. And then it would have a section on CUDA device synchronization. So that kind of boilerplate code in our environment, you will see later on how we can make use of this. And we can use our interactive C++ facilities to also synthesize most of that automatically, so that we can provide a relatively easy way to offload computations to the GPU, given our infrastructure. So I wanted to just show the people that were involved. We have over the years a bunch of very bright students who became mentors or who went to industry. They each of them contributed a good amount of code. Some of them are on the call. Some of them have their own careers, but heavily contributed to Clad. So the integration part of the automatic differentiation facilities that we have are in the two directions. First, the direction of the C++ interactive C++ interpreter Clang, which is an LLVM-based C++ interpreter, and secondly, on the data analysis software package used to process data in the field of high-energy physics called ROOT. Here I have prepared, in interest of time, an example how we can use Clad to generate a derivative on the fly through the C++ interpreter engine. So we can just start up Clang and attach Clad as a plugin. It is exactly in the same way how we attach Clad to the compiler, but here we attach it to the interpreter for interactive use. And we include the required header file, we define some function, then we call the relevant interface by specifying to which argument we want. Here in the case it's 0 because it's only one argument. And here one of the advantages is that we can also print the code and we can start executing the already produced code within the same session so that people can interactively type and test their code in a very similar to Python way. Here I'm showing another example which is a little bit more complicated. It is a sum of a function over, it is the sum function over a vector element. And we define a loop over all the elements, and we use the Clad concon gradient, which is the so-called reverse accumulation mode, where it is particularly useful for functions that take a lot of input arguments and return less output arguments. And in that case, we have a set of arguments in P, and we return a single argument. And here, the gradient function is very the reverse mode approach of automatic differentiation is very beneficial because it turns the computational complexity the other way around, depending on the output argument. So here we just produce the argument, and if we dump it, we will see that we'll have a bunch of code which is machinely generated, and it has a lot of details, but it does the thing that we were expecting it to do. The other thing that I wanted to mention is that we can use Clad as a service, which means that we will have a facility where we can embed in our framework and compile it with your favorite compiler and still have the ability to produce derivatives on demand. And here's how one can do it. So in that particular example, I have constructed a demo program which depends on the C++ interpreter, but this is statically compiled code. So we can just say interpreter declare what we just typed in the example that I was showing interactively in compiled code, and then use this facility which is called Clang concon value, and say interpreter process dfdx and give me back the function pointer. And this is the way how one can take a interpreter generated function pointer and use it in compiled code. So the result here, res, will contain the function pointer to the newly generated derivative. And here I'm going to just print it. dfdx at 0.1 is 2. And then you can see on the right-hand side, the example that this is statically compiled. That is a binary, which depends on, of course, on the interpreter and the automatic differentiation plugin, but it can be compiled and run with your favorite compiler and on your favorite platform. Another thing that I wanted to talk about is the current general benchmarks that we can do. And here my comparison would be against the numerical differentiation approach, which is the classical approach for many frameworks and tools, where we use in the numerical function, we use the central differences method, which requires 4 function calls to be able to compute the derivative at some point. So there are a number of disadvantages to that approach, which I'm not going to discuss here. And normally that's not the classical way how tools do it. They do more operations to stabilize the numerical results. Whereas when you have the automatic differentiation approach, the numerical stability is much better. And we don't need to do iterations because we will compute the gradient in one call. And on the right-hand side, you can see that here we just say Clad gradient of that function with respect to p, and then we can execute. So those are the functions that would give us the gradient functions for a given function. And that given function here is sum that you saw in the example before. Here you can see on the logarithmic scale, things are becoming much better using automatic differentiation. We can see that for higher dimensionality, we even can get up to 3,000 times speedups because of the fact that we don't call many times the function to be evaluated, and we evaluate all the things in one go. Another example that I wanted, and this work here is done by Alex Efremov, who was author on these benchmarks, and we recently redid it because they were a little bit old, and we wanted to make sure that things are still the way that they were in the past. The other approach, still the same setup. We have a different function based on Gaussian, a little bit more complicated here. And the performance benchmarks are still quite better in comparison to the standard numerical approach. Here we show around 900 times speedups, of course, with a high dimensionality of the input data. If we have less than, I don't know, 20 dimensions, we are not observing such speedups because of the fact that we still need to do some execution, and it doesn't pay off. We cannot really see the benefit when we have less dimensionality. So the software package root is a cornerstone for the high energy physics. It does a lot of things with numerical crunching and processing, analyzing data, including fitting probability density functions to the input data from different experiments at the Large Hadron Collider. The results that we observed after integration of Clad in root are very optimistic. We have integrated the computations, the derivative computations via automatic differentiation in a facility called T-formula, which is on the borderline between the interpreter and the compiled code. And here for histogram fitting, where you can have like a number of bins and then fit with a custom expression, we see substantial improvements. Here in the plot on the right-hand side, a lower is better. And here, the work, thanks to our person responsible for the mathematical package, he recently added a T-formula benchmark based on root that measures the numerical and the automatic differentiation approaches when we combine multiple Gaussians. And here we can also see quite impressive benefit by 10 times speedups, but we can go much higher than that. But our current optimizer, and of course any other optimizer, would need a second derivative to make smart choices. And for that reason, we will need the Hessian for to be provided. And so far, we have not done that. We plan to do it as part of this round of Google Summer of Code program. So we expect providing the Hessian to match what we saw in terms of speedups in the other plots. Future, Clad works for the cases that we have tested. They are not few, but still there are a lot of things that we need to explore, and a lot of codes that we need to process and make sure that we produce correct derivatives and also efficient ones. We also need adoption in the root package and beyond, but a gradual one, so that we can have like a loop where we start looking into possible use cases to support, and also we want to start getting back feedback how to improve the implementation or what's not supported. We also use Clad, and here Billy Moses did not mention Enzyme, but we also use both implementations to guide us in our very opportunistic, I would say, proposal to standardize automatic differentiation in C++. You can read our paper on this link. The other things that are ahead of us are full support of arrays due to some minor glitches or due to some minor implementation details. We do not support arrays well. That should be easy to fix. We are currently developing a error estimation framework, which is very interesting direction, because we should be able to estimate the floating point error computation based on applying Taylor series-like approximations, and having the adjoints computed by automatic differentiation would also yield big accuracy and performance. So this is a very interesting direction personally to me, and I'm really looking forward to see the results that will come up from Garima's sync soon. We also want to retarget on GPU code. We are currently working on that with focus on CUDA, but also we want to be able to include OpenCL and probably HEP. We want to support functor objects, because many frameworks have the concept of the computations that's stored inside a functor object rather than a simple function. We also want to make the derivation process explicitly configurable, so that we can say the way that the user wants the Hessian, how to be computed. Or we also want to look into possible integration with Enzyme. Enzyme providing a low-level access to the LLVM code may open some very interesting directions. And that being said, that's all I have for the moment. Thank you. Do you have any questions?
I wanted to ask about, you sort of addressed this, in the sense that you were talking about how this will integrate with root. There is, of course, a very large ecosystem out there of things we would like to auto-diff. And they extend across, C++ is obviously one of them. And they extend across tools like root, and they extend further across languages. And even worse, I think in the end, it would be nice to understand how they extend across systems. So I don't mean just a single program that you're running from the command line, but maybe it's a chain, a workflow, if you will. How do you see this fitting into that ecosystem? Has any thought been given how it will coexist with and I don't think anybody has a framework yet, so this is a bit premature for a detailed answer, but has some thought been started to give to how you might look forward to that?
Yeah, thanks for the question. It's really a great question. So in terms of C++, for example, in going beyond C++, I want to share that, for example, a recent proposal from the TensorFlow community was to actually allow TensorFlow computations and TensorFlow gradients to be computed in C++ rather than Python. So they will have an engine which from Python computes gradients to C++. So here it's one place where we can help. But more broadly, what I see is that there is a rise on tools, on automatic differentiation tools. And I think inevitably, we will have to somehow figure out how to crosstalk to each other, because each major framework comes with its own tool. For example, PyTorch has a dependence on JAX, if I'm not mistaken. Then there is other bunch of tools. For example, Julia come with their own set of tools, Zygote, I think. And at some point, there will be a need for people to crosstalk, to be able to have something that's a low-level tool that that makes the gradient computation or makes the transformation and then hands it over to the framework itself or to the higher level automatic differentiation tool. So I think this is a very relevant question here, and Bill and I have spent significant time to try to find a path forward. And Billy, feel free to interject. But my take is that the general direction should be, we should be trying to unify some way the implementations so that they can crosstalk.
Yeah, I mean, I think generally there's a couple of like key pieces that all of these differentiation tools provide. I think the bigger thing, and actually we're seeing a good amount of this as like an example from say the Julia community with like chainrules.jl, which tries to provide a general framework where all of the AD tools in there can like cross communicate. I think, you know, if there's a language that has multiple like different ways, like it's beneficial to have like one cross sort of interface. And I think the other sort of separate thing, which is partially why there's been like a fair amount of work inside of compilers and LLVM and cross-reaching tools and the like, is cross language then what's the equivalent of a magic interface that allows these things to interact. And you'll never be able to end up with one tool with like perfect information to work across all of the different levels, because like you'll end up with, again, something where you have like an algebraic rule that says this has to be 0 because I know like this specific algebra about it, or some either high level optimization alternatively. And the real key point is being able to like transmit that information across levels and being able to use like the benefits of all the different AD tools on the places that they work the best.
Thanks. I know of people starting to talk about this, and that's partly why I asked it here. And I apologize for taking it away a little bit from the direct subject you were talking about that there, Vassil. I find this work in C++ absolutely fascinating. So I'm really excited to see it progressing and opening up to the community. Thanks. It's a great talk.